Be here. I've been around for about 12 years. I came from the group of Paul Kellogg at Minnesota, and where I worked on some sounding rocket experiments with Paul and Jack Winkler. Who was incidentally Kinsey Anderson's PhD advisor. So these were experiments where we tried to inject an electron beam, an active electron beam, along magnetic field lines from the aurora. And in the case of Jack's experiments, the idea, and which worked successfully, was to bounce the electron beam at the conjugate point and measure the field line length, which worked very nicely. Paul's experiments, the idea was to reflect the electron beam off the auroral double layer, which didn't really work as we planned, but it was a interesting plasma physics laboratory when you put an energetic beam into a plasma. With varying current and energy and pitch angle distribution, you get a lot of interesting plasma physics. So the origin of my interest here is plasma physics. So Forrest asked me to talk about the heliosphere, or the heliospheric physics, and this, of course, has overlap with all the other topics. So when I think of heliosphere, I think of from the surface of the sun out to the heliopause, or maybe to the bow shock, and I think of the plasma environment of the heliosphere. Of course, there are the problems of the interaction with the planets, which Greg has covered already, apart from shocks. I'll say a few words about shocks. And there are problems associated with energetic particles that Bob has talked about. In fact, Bob and I didn't coordinate our talk, so I have a couple slides which are similar to his that I'll just skip over. But really, what interests me is the plasma physics primarily of the solar wind. So the solar wind is the region, is the plasma, the source of the plasma that fills the heliosphere. The idea is old, of course. It goes back to probably to Biermann or before. Biermann noticed comet tails that indicated there had to be an outflow, a radial outflow from the sun, and that suggested the solar wind. Parker's model of the solar wind, which everyone knows about, is basically like Bondi accretion with the clock running backwards. You put in a hot source of plasma at the base, and then it expands supersonically like a Laval nozzle. It goes through a sonic point and becomes energized out towards this. This is the wind speed versus radius. It doesn't have. There's no angular momentum. There's no electric field. When I say no electric field, that means that there's no. There are no exospheric effects in the model. So. This doesn't account for the fact that the electrons and ions would escape with different energies, and the magnetic field is entrained. So that means that there's a little picture here of the Parker spiral. The idea, of course, is that as the sun rotates, so if you start with a parcel of plasma moving outward with some speed, the sun rotates beneath it, and so any magnetic field line that threads this parcel of plasma and has its foot point in the sun becomes twisted out into an Archimedean spiral. Okay, so these features were predicted by Parker's solar wind model, and they're mostly observed. These are measurements by Mariner 2 that show the energy of the incoming beam being about 1 kilovolt, which is consistent with Parker. Okay, but what Parker doesn't predict, and what is still mysterious about the solar wind is, there are a couple of issues, but one is the generation. What is the source of heat at the base? So there are questions about what's the original source of heat input of the mechanical energy? Is the coupling collisional or collisionless? Does it proceed in a sort of AC way, that is by waves and turbulence, or by reconnection essentially? So you put in some mechanical energy, and it cascades up through an inhomogeneity. So there are propagation effects, generates turbulence, and if the geometry of the fields is right, it can reconnect, and then you could end up with what are called wave turbulence-driven models. So you're basically injecting magnetized turbulence at the base, and there are models that invoke turbulence or reconnection. So you have a lot of closed loops, you have a little bit of open flux, and where these points meet, you have reconnection. So the real question, all of these things are still questions. What is the source of the mechanical energy? How does it couple radially or rapidly into the plasma? How is energy dissipated? And again, are exospheric effects important? Is there a large-scale electric field that can participate in wind acceleration? Okay, so the solar wind is an enormous turbulence laboratory, and there's another point that's important here that essentially comes in here. If you look at the Parker solar wind model, you need to put energy in at the base, and that gives you an expanding plasma. But you, in fact, to match up with the observations of the temperatures at 1 AU, for example, you need to continually put heat into the system. So you need to dissipate turbulent energy as well. So there's a question of how energy is dissipated as the plasma propagates outward. So the idea again is that there's a turbulent medium. You put your arm in a bathtub and stir it around, and you'll get a set of eddies, and those eddies cascade. And there's the old idea of Kolmogorov that it's a scale-free process, that the cascading eddies couple to other eddies that are at similar scales until you get down to a scale where it dissipates, where the energy, the mechanical energy dissipates. And that's what introduces heat into the system. In a plasma, it turns out, because you have a magnetic field in a magnetized plasma, the symmetry of the problem is broken. And since your wave motion comes through Alfvén waves, you need a different kind of model of the cascade. And that model was introduced by Goldreich and Sridhar. And that model predicts that the energy cascades perpendicular to the magnetic field, that the primary source of energy, or the primary cascade of energy is perpendicular to the magnetic field. And recent observations with our stereo instruments, they back up that idea. So you have a power spectrum as a function of frequency, which is like wave number in the plasma, and that is a k to the minus 5/3 for the perpendicular spectrum. This is the angle to the magnetic field, so this is essentially perpendicular to B. And as you go to the angle parallel to the magnetic field, the spectral slope is different, and it's consistent with, it's actually k to the minus 2, which is consistent with Goldreich and Sridhar. So it looks like there's a perpendicular cascade. And that introduces another problem. If the energy cascades, this is a diagram of, this is k perp and this is k parallel. So if the energy is introduced here, by some stirring, by some arm in the bathtub, and it cascades in the perpendicular direction and not in the parallel direction, then you never get to the ion cyclotron frequency. And so you can't effectively heat your plasma, or you can't resonantly heat your plasma at the ion cyclotron frequency. But what we found, looking at measurements with cluster, was that the observations, now cluster is interesting. Cluster is not a heliospheric mission, but cluster is interesting because it has an electric field experiment on it. And heretofore, there haven't been good electric field measurements in the solar wind. But if you make electric field measurements in the solar wind, you can see the behavior of the magnetic spectrum. So the black line is the magnetic spectrum, and the green line is the electric spectrum. You can see them break apart. You can see that they're both sort of k to the minus 5/3 in the range where you expect them to be k to the minus 5/3, consistent with the perpendicular cascade, or any kind of fluid cascade. But when you get to shorter scales, you actually see the electric spectrum and magnetic spectrum break apart in a way that's consistent with the kinetic effects that you expect from a perpendicular cascade. So this is a strong line of reasoning that the Goldreich Sridhar, this coupled with the newer measurements on stereo of the anisotropy of the cascade, are strong arguments that we're seeing a Goldreich Sridhar cascade, and that and that at these small scales we're actually heating the plasma. So this is very likely to be the source of energy input into the solar wind plasma as it expands. Okay, but in some newer work, which actually is a little bit confusing in this light, we see something else. We see these are measurements from the WIND spacecraft. These are 1 million individual measurements of the plasma temperature anisotropy, so the perpendicular temperature divided by the parallel temperature as a function of the plasma beta. And what we see are these features. We see this sort of striking, swoopy feature. Dotted lines that you can't see on here show you where the instability thresholds are for the mirror instability in the plasma, and there's a dotted line on here for the ion cyclotron instability as well. And then down here is the fire hose instability. So at certainly in the sense of perpendicular compression, and in the sense of rarefaction for high beta, we see that the dynamics of the plasma are strongly constrained by in situ instabilities, by the fire hose instability. Actually, it's the oblique fire hose instability and the mirror instability. The bottom panel, which doesn't appear very well here, shows the magnetic compression, and you can see clearly that this is it's enhanced along the mirror instability threshold. So as the solar wind expands out into space, it's magnetized and it's trying to conserve its adiabatic invariance. So the ions are gyrating around the field, and they're trying to conserve their first adiabatic invariant, or if it's really a plasma, what are called the double adiabatic invariants, and that makes an initial distribution. So if you have a plasma distribution that looks like that's isotropic, so let's say this is the parallel direction, the velocity in the parallel direction, and this is the velocity in the perpendicular direction. If it's initially isotropic, where it's accelerated, and you propagate it out towards 1 AU, it should become beamed in this sense at 1 AU. And that kind of distribution function is unstable to the fire hose instability as it approaches this boundary. And so the middle panel shows the magnetic fluctuations mapped onto that diagram, and we see enhanced magnetic fluctuations all along the thresholds. So this is a strong indication, and these are really statistically significant results. We've got a lot of data here. This is a strong indication that the expanding plasma wind, the expansion of the wind itself, is driving turbulence in the wind. And this turns out to be interesting in the context of collisionless accretion as well. If you put fire hose into like a magnetorotational instability simulation, you'll see rapid growth of the fire hose instability as well. So this whole business, and there's some indication here that there's heating going on too, that as you approach the instability thresholds, you actually heat the plasma. So this is another source of energy input into the heat of the solar wind, but it's so prominent that it makes one wonder about a cascade. These models say that you should generate the instabilities, or put the energy in by stirring the bathtub with your arm and let it cascade down to viscous scales. But these models say that the energy is put in at the viscous scale. Okay, so now we're moving on to another topic. The models that I talked about are all sort of steady state models of solar wind evolution. But if you look at data, this is white light data. These are heliospheric images from the stereo spacecraft. So these are actually difference images. So what you're looking at is Thomson scattered white light. So it's like electron density with a 10 by 10 field of view. So the sun is here. You see occasional CMEs. You see large events that are prominent. But most of this is just the slow solar wind. So the solar wind doesn't really look like a steady. Oops, I want to go back. Doesn't look like a steady little evaporating gas. It actually looks like it's very blobby. It's very patchy. And it's patchy in a way that suggests magnetic reconnection. This is a simulation by Bill Daughton's group of a reconnecting current sheet. And so you see this is maybe not exactly right because it has periodic boundary conditions, but what you see is the formation of sort of blobs of plasma that escape, which is of course the old idea of reconnection from the sun. I think I have this picture again, and that in fact looks a lot like this. I mean, this is sort of anecdotally consistent with the idea of, instead of being a smooth, steady state evaporating gas, that you have small or some scale of reconnection on the sun that injects all this plasma. This has been observed, or reconnection is observed in the solar wind. This is data from a paper by Tai Fan. So Tai has done a lot of work on this. Jack Gosling, who's a former student, has also done a lot of work on this. What you see are let's just look at the magnetic field. These are magnetic field measurements from the ACE spacecraft, the cluster spacecraft, and the WIND spacecraft. And you can see the classic current sheet signature of reconnection. So you're crossing a current sheet with a velocity perturbation, which is consistent with an outflow, a reconnection outflow. And if you map these spacecraft are all separated by some 100 RE or so, you can actually infer a large reconnecting current sheet in the solar wind that has an extent of a few hundred. Actually, this is about 350 or 400 RE, Earth radii, across. So we do see evidence at 1 AU in the solar wind of reconnection, in addition to the compelling images, the white light images. Okay, I'm going to skip over this stuff because Bob did it already. But I will say something about this as well. So this is now another topic. These are the electron beams that Bob spoke about, which are generated thought to be generated in reconnection at a solar flare and escape along magnetic field lines into the heliosphere. One of the things that we see that Bob discussed, in fact, Bob showed this picture, is radiation. So we see what's called plasma emission, which is emission that's generated at the plasma frequency, the local plasma frequency, or its harmonic, twice the plasma frequency. And so because the plasma frequency in the heliosphere falls off more or less like 1 over r squared, as this electron beam propagates out into space, you see a drifting feature in the frequency domain. And that's what this shows you, the higher frequencies arriving before the lower frequencies, and then eventually you get the electrostatic waves. Because the magnetization of the plasma is so low, the cyclotron frequency is 1/100th or so of the plasma frequency, the electron plasma frequency. It's hard or almost impossible for a parallel beam to couple directly into electromagnetic radiation. So it has to couple first into an electrostatic mode and then into an electromagnetic mode from that electrostatic mode. And this is something that we saw on the WIND spacecraft. So the WIND spacecraft has really excellent instrumentation for this kind of plasma physics stuff. And so when you see these electron beams at 1 AU, this is maybe not easy to see, but you can see features that are beam-like, where the velocity space gradient of the distribution function becomes almost positive. You wouldn't really expect it to be positive because these measurements are made over seconds, and the growth time of the instability is milliseconds. At these times, you also see the Langmuir waves. On WIND, we have an instrument to measure the Langmuir waves directly. So these are large, what we thought were electrostatic waves, or what may be electrostatic waves, millivolts per meter. So there's a lot of energy density here compared to the radio emission energy density. But what was surprising is that the waves do not look like they're polarized longitudinally. They don't look like electrostatic waves. When the waves become big, we tend to see a polarization signature, which is not consistent with electrostatic. And so this led us to speculate that, in fact, the radio emission itself comes from the density gradients in the solar wind. So as the waves propagate, they disperse in density gradients and become electromagnetic by propagation effects. I think I'm going to go past this to the coronal mass ejection stuff. Bob already talked about coronal mass ejections generally. They're large magnetic flux tubes that erupt by some instability into the solar wind, carry a magnetic flux into the solar wind, and may actually help conserve magnetic helicity as they expand. These are early Skylab images. Some of the early work on this was done by Jack Gosling, who sort of characterized these, in some did some accounting on the observations. Our instruments on stereo. Oh, this is an interesting observation too. This is some work by Davin Larson, who used energetic electrons inside of a CME to measure the field line length and the twist of the magnetic field in the CME. In fact, Steve Kaler has a poster outside with similar work to this. So what you do is, when you have an electron burst inside of the CME, so the CME has this large twisted magnetic field. Those electrons are mostly or comparatively scatter-free because they're higher energy, and they propagate along the field lines. And when they get to 1 AU, you can measure their dispersed signature in time, and that lets you trace back to the source and measure the field line length. And so with this kind of result, or with these kind of measurements, Davin Larson used the WIND instruments to measure field line lengths of coronal mass ejections. This is some work by Ying Liu with our measurements on stereo, or with the measurements on stereo from the SECI suite. So what you're looking at are measurements from stereo B and stereo A. So the stereo spacecraft are two spacecraft. They were launched in late October of 2006 into a heliocentric orbit. So one of them is Earth leading, a little bit closer to the sun. One of them is Earth lagging, a little bit further from the sun than the Earth. And so in a sun-Earth frame, the angle between them opens up slowly over time. And what we're looking at here are images of, let's start this up again, of white light. Again, these are Thomson scattered white light effects. You can see features propagating away from the sun. These are just ambient features in the solar wind. And by tracing out the elongation angle, the intensity is a function of elongation angle, you can actually measure the speed of these little features that are embedded in the wind. And so Ying has done this and gets speeds that are consistent with solar wind speeds. So this is just the solar wind, blobs in the solar wind that are propagating out. These CMEs, the big ones, which Bob showed in his movie, also drive shock waves as they propagate out, and those shock waves irradiate as well. So one of the primary observations that we have between the sun and 1 AU is the radio emission. The radio emission occurs, it's in a frequency range. As I said, it's a plasma frequency, and that frequency ranges from sort of a few megahertz down to tens of kilohertz at 1 AU. That's all radio emission that's below the plasma frequency of the ionosphere at Earth. So you can't do these measurements on the ground. You have to do them from space. And measuring the frequency drift as a function of time of that type 2, what's called type 2 emission, is one of the primary indications of the speed of a CME and a shock as it propagates out in the heliosphere. So one of the things that we did with the WIND spacecraft was to look at the in situ observations as the shock passes over the spacecraft and excites an electron beam. We can actually measure the electron beam, measure the radio waves, measure the Langmuir waves all at the same time. And one of the things we were able to infer was that the electron beams occur, well, I'll just point at this picture, occur in little bays along the shock front. So we've known for a long time that the emission is patchy, and that basically corresponds to lots of little hot spots along the front of the shock as it propagates out. And so using the electron measurements, you can actually infer the sort of structure on the front of the shock. The shock, of course, is an interesting place in terms of plasma physics as well. At 1 AU, we were able to measure. It's long been known that if you fly a spacecraft through a collisionless shock. Now remember, a collisionless shock, it has to take directed kinetic energy and convert some fraction of it into heat. It has to slow down the flow and make heat behind it. But it's collisionless, right? So it can't do it by binary particle collisions. And so it does it by some plasma physics mechanism. But it has to do this with both the electrons and the ions. And because of the difference in the mass, the ion gyroscales are much larger than the electron gyroscales. So it's long been thought that the electrons move more or less adiabatically through a shock, while the ions are sort of trapped and gyrate in the shock, and that provides their dissipation. Well, one of the things we saw with stereo or with wind is that the electrons actually generate as they propagate through the shock using our electric field measurements. We could actually see the formation of what are called electron phase space holes. So we could see that the electron distribution becomes bunched up into phase space structure, and that phase space structure actually provides the dissipation. It correlates well with the temperature change in the shock. Okay, so this is my last science slide. We launched stereo in October 2006, and we launched it into what turns out to be the deepest solar minimum in the history of the space age. So the sun has been just dead quiet for a couple of years, and of course stereo was designed to be a solar mission. The solar wind pressure is down by some 10 or 15%. The radial component of the magnetic field is down by some large fraction. It's an anomalously quiet solar minimum. But one of the things that we did see, which is fascinating, are measurements that we infer as being due to dust, nanoscale size dust. So one of our instruments on stereo is a radio astronomy experiment designed to measure these weak signatures of type 2 and type 3 bursts. And so it's a very sensitive, very, very sensitive measurement. It has this background at the galaxy, basically, below the level of the galaxy. So we see the galaxy down to 100 kilohertz or so. And what we see often are impulsive, these little spikes. So these little spikes these are milliseconds. So this is 120 milliseconds, and this is the antenna voltage as a function of time. And so we see these little spikes in our data, and we see them when we launched. We saw them all the time. And we launched in October of 2006, and we were inundated by the little spikes and by the corresponding spectral signatures in our radio receivers. And then they stopped. And first they stopped on one spacecraft. And then a month later or so, or weeks later, they stopped on another spacecraft. And so we thought, well, maybe we have some problem with our electronics, or maybe someone else has a problem with their electronics, and we're receiving some interference from another experiment. So we jumped through all the hoops to try to figure that out. And then eventually, the noise started up again, first on one spacecraft, and then on another spacecraft. And it's episodic. It'll go for an hour or 2 hours and then stop, and then come on again for an hour or 2 hours and then stop. And then we started to think about dust. There were these measurements by Don Gurnet's group at Saturn, looking at dust in the ring. And so Don saw similar signatures to these, big spikes. Don's instrument is not as sensitive as this one, so he sees big spikes of that correspond with crossing of the dust ring, and he interpreted it as dust particles hitting the spacecraft. And in fact, that's exactly what we think we're seeing here too. So what happens is that a dust particle hits the spacecraft and basically ablates. So you have the dust particle coming in at some velocity, and it makes a kind of plasma cloud. And there's a known relationship in the laboratory between the charge liberated and the mass of the dust particle and the speed of the dust particle. So there's a known, fairly tight curve that predicts the liberated charge. And of course, when that charge is liberated, it produces a small perturbation in the voltage, the floating voltage of the spacecraft. The spacecraft is like a Langmuir probe. It's sitting in the solar wind, and so it's charged up because it has photoelectrons. It's emitting photoelectrons, and then it charges up positive, and it attracts back thermal electrons and sits at some equilibrium potential. But if you perturb it, its potential will oscillate. And because on stereo we have a measurement in our sensitive radio frequency measurement of the single-ended voltage. In the past, these things were typically done by just taking a differential measurement, which reduces common mode noise. We have single-ended measurements. We can actually see these little spikes. And if we take the voltages of the spikes, actually in the spectral domain, the voltages of the spikes are consistent with masses and speeds. So the masses correspond to sort of order of a few nanometers radius, with grams per centimeter cube mass densities, and the speeds correspond to something on the order of the solar wind speed. If we put these numbers in, we get charges that give us the right order of magnitude for our observed charge, and we get occurrence rates of the dust impacts that more or less lie on the power law of the corresponding measurements at higher mass. And so what it looks like we're seeing are sort of nanoscale dust particles that are charged and that are picked up by the solar wind and energized up to sort of solar wind speeds and then impact the spacecraft. And there's one other observation which fits nicely with that, and that is that we have these two spacecraft and they have different sort of orientations. Let's say we have one that has antenna A here, antenna B here, and the other one has antenna B here and antenna A here. And we tend to see that the biggest signature on the face that is the ram direction. So let's say the spacecraft are moving in some direction with respect to the sun. So there's a ram face and an anti-ram face, and we tend to see the larger signatures on the ram face, on the antenna that's adjacent to the ram face of the spacecraft. So this is all, in spite of the fact that there's hardly anything going on in the solar wind. It's a very quiet time. If you want to study solar wind plasma physics, it's good. But if you want to study impulsive heliospheric physics, it's not so good. We're also seeing what we think are some exciting new observations of dust. Okay, so I think this was going to be my little list of SSL heliospheric missions. I think I left out OGO here, and I hope I didn't leave out any more. But my life sort of starts in here, so I apologize for my myopia. So we have, at the moment we have the wind and stereo spacecraft up, providing lots of really great data in spite of a quiet solar minimum. And as Bob said, in the future we have hopes to put instrumentation on the ESA Solar Orbiter mission and the NASA Solar Probe Plus mission. And it's, as Bob said as well, there's the Sentinels mission, which is just now off the horizon a little bit, but the horizon will eventually come into view. Okay, that's it. Thanks. Questions? Steve?
You showed the movie of the blob from the wind.
Yeah. Yeah.
You mentioned that there were some CMEs in there.
I think
I was just wondering if you'd never seen chronograph images and never heard about CMEs. Look at that movie and think, well, there are large-scale structures and small-scale structures.
Well, that's a good question. I mean, knowing the flux tube model of the CME. I mean, when I see this, I think I see things with helical symmetry at some angle occasionally, and so that's what makes me say that there are CMEs in there, like that, for example. But I mean, if I were going to go at this data myself, I'd probably try to do some kind of pattern work on it to see if I could pull out a geometry. Any more questions? Steve?
Just say again, I think I missed it. How do you differentiate your particles? Your little small and fast and not big and slow?
For the dust? Okay, so for the dust, it's the argument is this. The argument is that you have a known relationship between the mass and the speed, and this index is essentially 1. So given some velocity, you expect some charge, and then you make a measurement, delta V, which is just through the capacitance of the spacecraft to infinity, and so you can relate and there's some efficiency on charge collection. But the charge is small compared to the floating charge of the spacecraft, so the efficiency is pretty large. So you get some delta V signature that you can associate with the delta Q. And so you can compare this with some expectations here. But then in addition, we have the measurement of the occurrence rate of the stuff. So let's go back to that slide. So the bottom panel here shows. Actually, this is in heliospheric longitude, so this isn't quite right. Another thing that we see is that the dust storms often coincide with known meteor streams. But you can basically do a count rate, number of events per second. You can compare that to the observations at larger masses, and we seem to fall in there. There is one observation from the space station of an exposed plate, which detected nanoscale dust at an occurrence rate that's comparable to ours. So now, the thing to do now is to understand, this is only consistent with our data if we have a speed which is consistent with pickup. So the dust is charged. We know that it's charged. If its charge to mass ratio is low enough, then it'll be picked up by the solar wind and energized, accelerated. So now the thing to look at is to try to correlate that with magnetic field, electric field essentially, to see if there's any V cross B orientation, because the gyro radius of the dust is enormous. It's a large fraction of an AU with these assumptions. Okay, if there are no more questions, then I think that finishes this session right on time. We start again at 1:30, I believe. Yeah, 1:30. So lunch is at 12:30, and remember there are more SSL tours starting at 12:30, starting now as well. So let's meet back here at, let's say, 1:35, and we'll start the next session.
The lunch is served up at the Space Science Lab, not out here.
Oh, that's right.